Hello, Year Sevens. What is going on? We are back for another Friday flashback, or as some of you are calling it, Friday. Why the heck do we have to do this again day? This time we're casting our mind all the way back to last term when we were locked up at home previously, when we were learning fractions and decimals for that whole term. We're covering the most important part of our fractions topic, which is equivalent fractions, because if you can't make fractions equivalent, it's really, really hard to do any of the other maths associated with it. It's really handy for maths class, for cooking class, all kinds of other classes, measurement classes as well, just to be able to turn one part of something into an equivalent part of something. All right, so the basic idea behind an equivalent fraction is to be able to have a fraction and express it in a different way, but still have the same fraction, right? We've got an example of that here. We've got two very talented, very intelligent individuals comparing equivalent fractions with each other. We've got this one here, oh captain, my captain, who says we've played one half of a game. And then we've got this extraordinarily talented player who I basically named my son after, even though he debuted after he was born. He's giving us another fraction. Right, this guy says we've played half. Right, we must be at half time. Happy to have a rest, I guess. And this guy says we've played 2/4. And whether they know that they're doing it or not, what they are essentially doing is giving equivalent fractions, because if you've ever seen a game of football, maybe not all of you have, but you'll get the idea that both of these players are celebrating halftime, right? One half and 2/4 are the same thing. And that's all equivalent fractions is about, being able to take part of something and express it in a different way. And unfortunately, right, not implying that there's less intelligence going on here, basically because we're outright saying it, not everyone can do it. And usually if you put on a jumper with a yellow sash going down the middle, you probably can't do equivalent fractions. When dealing with equivalent fractions, I think it's really, really important that we are able to visualize what's happening here. And the most important part of it is recognizing that when we change the way our fraction looks and when we express it differently, give our fraction a different name, we're not actually changing the size of what we're dealing with here, right? So here is a pretty clear half because we've got two pieces and one of them shaded in. Making an equivalent fraction is basically as simple as changing the amount of parts that my whole is cut into, right? So if I'm cutting it into more parts, so now we're dealing with quarters instead of halves, right? You'll notice the shaded amount doesn't change, right? It stays the same. The same proportion of my circle is still colored in. Half of my circle is still colored in. But now we're dealing with a fraction where my whole is cut into 4 pieces instead of 2, right? That means that an equivalent fraction is out of 4 instead of being out of 2. And if I look at how many is shaded in, it's 2, right? So my fraction looks different. There are different numbers involved, but the actual size of the fraction hasn't changed. I've just got more pieces, right? I've got more pieces in total, so I need more shaded in. All right, so we'll take that another step. I've got to put a line, we'll go around about through here. We have to do it through here as well to make sure all the pieces are the same size, otherwise it's not a fraction. And now I've got 1, 2, 3, 4, 5, 6, 7, 8. Looks like a pizza. Right, so if this is my pizza and I eat the shaded pieces, right, there were 8 of them, and I've shaded in or eaten 4 of them. Right, so again, equivalent, equivalent, equivalent. We can take it to the nth degree and go again. I'm just basically doubling the amount of pieces again. All right, so you see I've got lots more pieces. But that means every piece of my whole thing is smaller, right? They're all smaller pieces now. So to have the same amount in total, to have half of my circle, because I have even more pieces, I have 16 pieces now in my circle, that means I need to have 8 of them shaded in, right? But as the numbers get bigger and bigger and bigger, it doesn't mean I've got more of my circle. It just means I need more pieces to have the same amount shaded that I started with, right? A half, 2/4, 4/8, 8/16. They're all the same thing. And generally, while diagrams are really useful things to have, quite often this idea is introduced with things like fraction strips, which some of you might get to work on today. Generally, we have to learn how the numbers work, so we don't need to have a diagram behind us, because once we can visualize it in our heads, we have a faster time of kind of just working with the actual numbers behind what's going on. So the definitions are here. You've seen this slide before. Some of you will have written in your glossary. Generally, the idea is that fractions that have different denominators, but they're still equal, they're called equivalent fractions. So these are the equivalent fractions from earlier. And we can find any equivalent fractions as long as we're consistent between the top and the bottom of our fraction, and that's through multiplying, or it's through dividing if I'm simplifying. So generally, do whatever you want to the bottom of a fraction, right? Usually I'd call someone out and I'd be like, just times it by anything. And someone would be like, times it by 100. So I would. If we put a 200 there, I can still keep this fraction equivalent and keep it the same, right? I times 100 here, as long as I times the top by 100 as well. Because it's basically saying I'm cutting my whole thing, right? The size of the thing I'm cutting up hasn't changed, right? Same size pie, same size pizza, same size whatever. If I cut a pizza into 200 pieces, I have to eat a lot more to get full, right? A half is the same as 100 on 200, and I know it's the same because I did the same thing to the top as I did to the bottom. So another thing I think is really important is just for you guys to be able to check that your fractions are actually equivalent with each other. In case, you've done an answer and you might have got it wrong. It doesn't hurt to just have a second look at something and just make sure you've done the right thing. So it's always good to think about kind of the in-between numbers, kind of between the tops, between the bottoms. I like to think about it that way sometimes, to just think, what number is in between these two? In terms of my times tables, through timesing or dividing, just what is the in-between number that turns one of them into the other one, right? So if we're looking at this example here, 5 into 35, we refer to our times tables. We know that 5 times 7 makes 35. Then I check the denominator of this fraction, 8 into 48, and in my times tables I know that 8 times 6 is 48. So the top of this fraction is being multiplied by a different number than the bottom of this one. So if this was the kind of question we were being asked, we would have to say that these two fractions are not equivalent. Right? They're not the same as each other. They're not equal at all. Right? These two fractions are not equal. Let's have a look at this next one down. Right? So 9 into 63. We love our 9 times tables. 9 times 7 is 63. We like our 7 times tables less, but most of us have memorized that 7 sevens is 49. Right? I went times 7 and times 7. That actually means these two fractions, even though they look different than each other, are exactly the same. These are equivalent fractions. These fractions are equal. Right, so we've actually answered this question properly if this was an answer we gave. With the last one, okay, this is tricky, right? 3 into 16, I don't know what goes into that, right? That's timesing it by 5 and a bit, right? It's kind of 5 point something. It's actually 5.333, but whatever. It's 5 point something, right? This is about 5 times bigger, and this bottom one is not even 3 times bigger, right? 3 sevens is 20, right? We don't have to look that closely to figure out the top is being times by 5 and a bit. The bottom is being times by 2 and a bit, right? These are definitely not equivalent because this top number has been multiplied by much more than the bottom number. So even though we can't see exactly what numbers go into it, we should be pretty clear that these two fractions are not equivalent and not equal, and they have nothing to do with each other, basically, right? Not equal at all. Right, so then the question is, like, why is it so important that we learn equivalent fractions? Because we did spend like a whole week on it back in term 2. It's really just fundamental stuff because when we do our work with fractions, we're either kind of adding, subtracting, comparing, doing things like that. You can't do any of that unless you can make fractions equivalent first, because you need something comparable, right? Once we actually get our fractions equivalent or with the same denominator, then we can do maths pretty easily with them. Because if I want to add 3 quarters and 2 quarters, well, that's just 5 quarters. Right? I can make it into a mixed number if I want, but it's basically as simple as saying I've got some quarters, I've got some more quarters, that's how many quarters I've got, right? So if I start with a different denominator, as long as I can make them into quarters somehow, then this part's easy. Same for subtracting, right? Once I've made my fractions both into thirds from whatever other number they might have been, 7 thirds take 5 thirds is just 2 thirds, right? But we quite often can't do this unless we make them equivalent first. Right? It's also good for comparing, right? Understanding how two values compare with each other. Because let's say I'm offering you a block of chocolate. I'm either offering you 4/9 of my block of chocolate or 3/7. You want to know which offer to take me up on, right? And you're guessing at the moment because you don't know. You know that both of these values maybe are less than half because it's kind of a small amount of my whole. But unless you make them into, in this case, 60 thirds, because 9 and 7 do go into 63, right? I have a look at them, right? This one, timesing 7 is 28 60 thirds. This one here, you got to times by 9 to get to 63. So times the top by 9, this is 27 60 thirds. right? These numbers are different. One of them is now clearly bigger than the other one, so you'd be mad not to take me up on my 28/63 or my offer of 4/9. Okay, so just being able to compare two amounts of something with equivalent fractions is really important. You don't want to get ripped off and miss out on 1/63 of a block of chocolate, all right? And just having this conceptual understanding, right, that objects, whether they're fractions or real life things, right, apples and oranges, objects get grouped up and classified and sorted out, plus, minus, whatever, when they are the same, right? We don't add apples and oranges, so we don't add thirds and quarters, right? But we add quarters and quarters, we add thirds and thirds, all right? So just understanding that things should be the same so we can deal with them is just very, very important, right? So hopefully this is refreshing your memory. Okay, we've got a bit of work to just revise you on this concept, which is very important. Good luck with it, and we're out there in the Google Classroom and the Google Meets and on Zuno if you need help with this.